part 2 of the video. Sorry for running out of batteries. So if I look at the top here, ignore the picture on the blackboard for the moment because I can't keep it straight. I find these two elements, these that are in pink boxes labeled with stars, and I discover that the one on the left is smaller. Now, if I look, for example, at this pair of elements in row 1, the one on the right cannot be the smallest element in its row, because then I would have a minimum of that 2 by 2 matrix that's to the right in an earlier row and to the left in a later row. And so all of the entries in this matrix that are above the thing on the right are dead. They cannot be the smallest element in their row. So with one comparison, I can knock out, in principle, most of a column. The other possibility is that I discover that between these two start elements, the one on the left is the one that's bigger. And by a symmetric argument, all of the elements immediately below that entry on the left are dead. They cannot be the smallest element in their row either. Yes? So far I've been talking about, assuming that all the elements are distinct. If you want to allow ties in your matrix, when I'm talking about the minimum element, I mean out of all minimum elements, the one furthest to the left. Okay, so break ties by the column index. Yeah?
Second example, why does having another maximum below the first star, violate
because if you, for example, if this were a row minimum and that were a row minimum, this 2 by 2 matrix would be bad.
You're doing minimum now, not maximum. Okay.
It's always minimum. It's always minimum. Always minimum. Which is probably why I got screwed up over there. Okay? So, with this idea in mind, that with a single comparison, I either rule out one entry in every row above, or I rule out one entry in every row below. Right? So I'm going to use that to design this algorithm called reduce. And what reduce does is it takes a matrix that's totally monotone, and it has more rows, more columns than rows, so it's wide, it's short, and it turns it into a matrix that is square, and is still totally monotone, and all the row minima in the original matrix survived into the new matrix. Okay, so it kind of does a horizontal compression of the matrix. And the way it does it is by identifying certain columns that are completely dead, top to bottom. So in a single comparison, I either rule out the top half or the bottom half of a column. But by combining multiple comparisons, I may be able to rule out entire columns. And then what ends up actually being returned here are the indices of the few columns that survive the winnowing process all the way to the end. Okay. So rather than walking through the technical details of this algorithm line by line, which, as you could probably guess, I will probably mess up, I'm just going to show you, pictures of the algorithm in progress to kind of explain intuitively what's going on. And if you want to see the technical details, they're written in the notes, although honestly most of the area on the page devoted to the explanation is taken up by these figures. Okay. So here I have I'm jumping into the middle of the algorithm. So what information am I maintaining here? The first thing I have is an array that it actually functions as a stack called S. That's just a screensaver. Okay. That contains, so there's kind of a current column K for current and K for column. And some of the columns to the left of K are completely dead, and some are not. The ones that are not are indexed in this array S, from left to right. Okay? So this column is dead, these two columns are dead, this one's dead, this one's dead. In each of the, in each column S sub I, the top I minus 1 entries in that column are dead. So nothing is dead in column S1, one thing is dead in column S2, two things are dead in column S3, and so on.
Is that some guaranteed properties?
Yeah, so this is in fact a loop invariant that the algorithm is going to maintain. Okay? Now, I look at the highest live entry in the column on top of the stack, the last live column to the left of K. And I look at the corresponding entry in the same row in the current column K. And there are two possibilities for what can happen. I do the comparison, and I'm going to cheat. See, I actually drew the picture down here. One possibility is that I discover that the star on the left is smaller than the star on the right. So what happens in this case is, well, clearly this entry is ruled out as a row minimum. But then it also turns out that every entry above it is also dead. And so I've thrown out most, but not necessarily all, of column K. Okay, hang on a second. And at this point, I can declare, notice I found just past the sixth thing on the stack, which had 5 dead entries at the top. I now have another column that has 6 dead entries at the top. So I'm going to push this onto the stack, calling it S7, and then I'm going to move K to the next column. And now I've restored my loop invariant. Again, everything to the left of column K is either dead or on the stack, and anything in position I on the stack, the top I minus 1 things are dead. Okay. The other possibility is that I find things going the other way. Right? The start entry on the left is bigger than the start entry on the right. In this case, start entry on the left cannot be the smallest entry in its row. And moreover, nothing else lower in that column can be the smallest entry in its row either. Which means at this point, I've discovered column S6 is dead. And so I pop that off the stack, that index off the stack. K stays the same, but then my next comparison is going to be between these two entries. And again, because this is the last live row on the stack, this is the highest the highest live entry in that column, and this is the corresponding entry in the same row of K. Right? And again, at this point, I've restored the loop invariant. Every column to the left of K is either dead or it's on the stack, and the ith thing on the stack, the top I minus 1 things are dead. Okay? So, in short, to sort of summarize what happens here, in every every iteration, I'm just going to repeat this. I'm going to repeat this algorithm until k runs off. Either k runs off the right edge of the array, or I have pushed, I sort of pushed the current column all the way to the bottom, the current row all the way to the bottom. So you either kill a column. And that can only happen the number of times equal to the number of columns. So this can only happen n times. Or I push a column onto the stack. So how many times can I push something onto the stack? So, in other words, how many times can I execute this pattern? Yes?
Number of rows?
Well, close. Because the idea is every time you push something onto the stack, you'd like to say I can only do this the number of rows times. Because every time I push something onto the stack, I move down to a lower row. The problem is that I push things on and later I might pop them off and I go back up. But everything I push on has one of two possibilities. Either it survives to the end of the algorithm, and then because of the loop invariant, the number of live columns cannot be bigger than the number of rows. Or it gets popped off, and we already counted those. Right? So in the analysis, this happens at most m times, at most n times, because they're n rows. And this happens at most m plus n times. Because when I push, either I'm going to be one of the m columns that survives to the end, or I'm going to be one of the n things that gets pushed off. And in every iteration of the algorithm, I literally am just doing one comparison and then some bookkeeping. Right? So the overall running time of the algorithm is linear. In order n plus m time, I changed my matrix, my totally monotone matrix, which is really wide and short, into a square matrix. The number of rows, the number of columns that survive this filtering process is always less than or equal to the number of rows. Okay. So if I go back to my divide and conquer algorithm, the way that this divide and conquer algorithm worked is at every iteration, I cut the number of rows in half, but the number of columns stayed the same. And because the number of columns stayed the same, I get this annoying log factor that shows up in the running time. So what I'm going to do instead is the actual smoke algorithm combines these two. So I'm given this two-dimensional array M. If the number of columns is bigger than the number of rows, I apply this filter to M. And then I do this even row recursion from before. Okay. So if the array is wider than it is tall, apply this filtering algorithm to narrow it, and then take every even row, recursively call smoke to get the row minima in every even row, and then walk through the staircase to fill out the odd rows. And now the running time recurrence for this turns out to be one of two things. This is, so m over 2n if the array is tall, meaning m is bigger than n. And the other The other case is if m is less than n. Okay. So if I have a short array, I need order n plus m time to do the filtering. But if m is less than n, then n plus n is the same as order n. Right? I've swallowed at most a factor of 2 in here. And then I recursively call the smoke algorithm on the resulting matrix, which is now just m over 2 by m. Filter brought it down to an m by m matrix, and then I take every other row in that, I get an m over 2 by m matrix. And then I need to walk back up in that filtered matrix and walk through the staircase that again is only going to take me order n time. If the array is tall, then I don't bother to do the filtering, which means I just take every other row, but I keep the columns, all the columns, and then walking through the staircase again is going to take m plus n, but because m is bigger than n, I can simplify that down to order n. And then plugging all this into a more or less mechanical induction argument implies basically I'm going to be in the first case until the matrix becomes square, and then I'm always going to be in the second case. And so notice in the second case, n vanishes completely from the recursive arguments. Every time I recurse in a matrix that has half as many columns and half as many rows. And so I get a nice descending geometric series that eventually vanishes. Yes?
Before you run this, the matrix is already completely built, right?
Yes. I'm given a complete m by n matrix that I know is totally monotone.
But when you fill it, doesn't that take time also?
I'm sorry?
When you're solving a dynamic
I'm given an m by n matrix. This is not, and again, I'll repeat this point that I made earlier, but it may have gone by too fast. This matrix that I'm searching here is not the memoization data structure. It's some other implicitly defined two-dimensional array that is what the two inner loops in the dynamic programming algorithm are really searching. Right, so you have to look at the dynamic programming algorithm that you've written down and look at the two inner loops and see, what am I considering for I for j? What is the value how does the value depend on I and j? That defines implicitly a two-dimensional array indexed by I and j. Okay, that's the matrix that I'm talking about. Now, there are circumstances where, in the shortest path example, right, I explained how one might get one of these matrices. And it really was the case that in each iteration of the outer loop, I can sort of write the whole matrix down and do the searching. There are other dynamic programming algorithms where you have to compute the matrix one row at a time. And then this algorithm doesn't work, but there's another more advanced version of this algorithm that can still find the minima in the rows even when the rows are revealed one at a time in only n plus n time. All right. Yes?
What kind of problem would result in a fully monotone matrix?
I'm glad you asked. So, most of the time when we see totally monotone matrices, the matrix actually satisfies a stronger condition than just total monotonicity. Okay, which is called the Monge property. So Gaspard Monge was a French geometer who lived in the late 1700s. He was, among other things, interested in constructions of dikes and dams and ship channels and earthworks. And so one of the problems he considered, which we'll see actually later again in the course, is I've got a pile of dirt here, and I want to move that pile of dirt over there. What is the cheapest way of doing that? And what he meant was, I want to take every particle of dirt over there and find a place to put it over here. And assuming that every particle of dirt travels in a straight line, what I want to minimize is the sum of all those lengths. Okay, it's a bit weird, but this idea of moving mass from one place to another is really the basis of what we'll later run into as maximum flow algorithms. It shows up in operations research as either assignment problems or transportation problems. And in particular, the picture that shows up in Monge's treatise is something that looks like this. It says, let's take 4 points in the plane, in this picture, and you can connect them by 2 straight lines, or you can connect them by 2 lines that cross. Now, in fact, there's actually a third way that you can connect these, but let's imagine that over here on the left, these are particles of dirt, and over there on the right, these are places that they're going to go. Then the length of the red segments is less than the length of the green segments. All right? This is by the triangle inequality. So if I follow, for example, that path by the triangle inequality, if I go from upper left to center to upper right, that's longer than following the red segment at the top. And symmetrically, following the green path up and then down, that's longer than the red segment on the bottom. So altogether, the red segments together are shorter than the green segments. Okay. Now, just to be concrete, let me imagine that these are points along some curve, and these are points along some other curve. And I'll just sort of index these like so. Then the property that you get here is that the distance from point I to point J plus the distance from I prime to J prime is less than the distance from I to J prime plus the distance from I prime to J. D, that distance, if I have n points on the right and m points on the left, that defines a matrix. That matrix is called Monge if this inequality holds for all indices I less than I prime and j less than j prime. Okay? That's what a Monge array is. It's an array that satisfies the same conditions as Euclidean distance. Okay? Now it turns out it's actually quite easy to prove that every Monge array is totally monotone. Right? If the only way to violate total monotonicity is for Dij prime to be bigger than, Dij prime to be smaller than Dij. In the upper row, the minimum is on the right, and Di prime j to be smaller than Di prime j prime. In the lower row, the minimum element is on the left. But now I violated Monge by just adding those two inequalities. Okay, so Monge implies total monotonicity. Okay? So Monge arrays show up in lots of contexts where the problem is, the underlying problem is geometric. So in particular, if you're computing some shortest paths using Bellman-Ford, and the vertices are like points on a circle, then in fact the inner loop, you're going to be looking for the row minima inside a Monge matrix, and you can reduce that order mn to something smaller. Okay. Now, the interesting thing is that unlike total monotonicity, which is a very sort of loose and floppy condition. Being Monge is actually a little bit rigid, and that rigidity helps in figuring out, when a matrix is Monge. So it actually suffices to consider adjacent rows and adjacent columns. So in the definition of Monge, as long as you just substitute in I prime equals I plus 1 and j prime equals j plus 1 in that inequality, if that holds for all I and j, in other words, if you just look at contiguous 2x2 matrices and you verify the Monge property for those 2x2 matrices, it actually implies for all, bigger 2x2 matrices that aren't contiguous. And this is just a straightforward induction proof. Which means I can check that a matrix is Monge in linear time, in time proportional to the number of entries. Another interesting condition that you can have is that when matrices are Monge, this is not something that's going to come from a distance matrix, but if all the entries in every row is constant, then this matrix is trivially Monge, because I should actually say this is less than or equal to in the definition, because you actually get equality there between those two pairs. Likewise, if I consider a matrix where every column is constant, that's going to be Monge, and therefore totally monotone. And the last sort of weird case is that if the entire matrix is 0 except for some upper right quadrant that's only equal to 1, that matrix is Monge. Or similarly, if a lower left quadrant is equal to 1. And then finally, Monge plus Monge equals Monge. So if I have two Monge arrays, and I sum them together, I get another Monge array. And if I take, alpha times Monge, where alpha is any positive real number, I'm going to get something that's Monge. So if I double everything in the matrix, it's still going to be Monge. And this turns out to be an exact characterization of the Monge arrays. Every Monge array is a sum of multiples of matrices that have constant rows, matrices that have constant columns, and these upper right flag matrices. Okay. Now, that's not the characterization that you would normally use to say, hey, look at my dynamic programming algorithm, the underlying matrix is Monge, and therefore I can apply the smoke algorithm. Typically, you would just check that inequality in the definition for contiguous 2x2 matrices. You would just argue for every 2x2 matrix where the rows and columns are contiguous that this inequality is satisfied just directly. Although it does sometimes help to observe that the matrix you're searching can be decomposed into two parts, and each one is Monge, and you add them together. And so if you run into a dynamic programming algorithm where there's some kind of underlying geometry in the optimization, say, for example, problem 2 on the next homework, by walking through the details of applying those conditions, you can show that the inner pair of for loops can be substituted with the smoke algorithm, and then you can shave off a factor of n from the running time of the algorithm. Okay? I know this is a little abstract. I'm still writing the notes of the Monge part, but I'm going to try to have a concrete example in there, which hopefully will be posted within the next couple of days. Yes?
So is the definition of Monge for the any matrix or just square?
Any matrix. It does not have to be square.
Just curious, does Monge times Monge give you anything interesting?
No, not really. The problem is that a Monge array can have negative entries in it. Right, if I have, just a column of -1s and everything else is 0. And then if I multiply, everything just goes out the window. Unfortunately, the element, if I take two Monge arrays and I take the minimum, in every element, I take the minimum of the entry in A and the entry in B, that doesn't give me anything interesting either. On the other hand, interestingly, if I take, every Monge array is totally monotone. If all the entries in the Monge array are positive, it's still totally monotone. If I square all of those entries, it's not Monge anymore, but it's still totally monotone because all the entries are in the same order that they were before. And total monotonicity only depends on order. So you can still apply the smoke algorithm if it's just something derived one step away from a Monge array. One place that I want to point out in particular where this kind of cost savings actually shows up in practice and actually is incredibly useful, practically speaking, is in sequence alignment and sequence reconstruction problems in molecular biology. So the kinds of things that you would do with edit distance that resemble actually a little bit more closely problem 1 in the current homework. If instead of the cost of one of these chunks where you have an up arrow followed by k symbols, instead of that costing just delta plus k, it costs, I don't know, square root of k. So it gets slightly cheaper to insert longer substrings. Then in fact, the underlying dynamic programming matrix has a structure that looks similar to this. And so you can speed up the dynamic programming algorithm, which means that it only takes minutes to do sequence comparisons of multi-billion base pair strings of DNA instead of eons. Right? A factor of n when n is a billion matters. So this discovery of being able to exploit a monotonicity structure in the dynamic programming matrix is really incredibly important to getting fast dynamic programming algorithms in that biological context. So if any of you are doing bioinformatics, you really need to know this. Yeah. Sure.
So when you are shrinking the N matrix into an N matrix,
This stuff? Yeah.
So what do you do when you reach the bottom and some columns?
You throw them away. Once the starred row gets to the bottom of the array, at that point the algorithm is done. You know that everything further to the right is dead. That requires a bit of proof, but. Any other questions? Yeah.
After you do the filter, don't you already have all the minimum stat?
No. So what filter does is it just throws away columns that don't matter. But I still don't know, for example, after I filter this array, I still don't know what the minimum entry in this row is. I know it's in one of these five or six columns, but I don't know which one. So what I actually end up with is a square matrix where I know that everything above the main diagonal is dead. But that's not really enough information to help me.
It's O(n plus m) the best you can do for a matrix total
Arguably, in order to output the minimum element in every row, I have to look at every row. And I think one can also argue that to find the minimum element in every row, I have to look at least one element in every column. So n plus m is the best you could hope for. I mean, it's not, it's actually a very good question, because I'm already in the situation where I'm not even reading all of the input. Right? The input is an m by n array, n times m. Most of the array I'm not touching at all. I never look at it. And so it's not at all obvious that this is the best that you can hope for, but I need to double check this, but I believe, yes, it is the best that you can hope for without some further additional assumptions. Yes, in the back.
Shouldn't there be a log factor in the log n by n?
No, there are no log factors in here. So the reasoning is that when I'm in this regime, every time I recurse, m goes down by a factor of 2. So I get a descending geometric series. And when I'm in this regime, in every iteration, n is going down by a factor of 2. So I get a descending geometric series. So the logs just vanish. Last question.
The second one is an n first, and you start n and then geometric.
Yes, but addition is commutative. So, yeah. First you decrease m, then you decrease n. Yeah. Okay. Thank you, and thank you for being patient with the technical difficulties.